Hello, my name is Brian Rose, and welcome to this introductory lecture on climate modeling for the Climate Match Academy. A few words about myself before we dive into the content. I'm a climate scientist and associate professor at the University at Albany in New York State, USA, originally from Canada. My work is in global climate dynamics and modeling, and I'm broadly interested in physical processes in the atmosphere, ocean, and ice that regulate climate on this planet in the past, present, and future. I'm also particularly interested and passionate about open science and open source software and contribute to a number of open source projects. I am the author of an open online textbook called The Climate Laboratory, which actually served as a key source for some of the Climate Match Academy exercises. And I've been very active in Project Pythia, which is an open community learning resource for Python-based geoscientific computing, and hopefully a good resource for many of you working through the content of this course. So this is a lecture on climate modeling, but I'm actually not going to start with models. I'm going to start with the Earth itself and talk about the energy budget of our Earth system. How does Earth exchange energy with its surroundings? Because as I'll dive into in this lecture, that's really at the heart of what climate models are there to represent, are these global flows of energy. So we'll spend a little bit of time on a kind of complicated figure here that comes out of a recent IPCC report. And this is a schematic showing, with numbers showing our best current estimates of a number of key processes in the global flow of energy. And this is kind of separated into two sides, labeled solar and thermal. And these big arrows represent fluxes of radiation. And so the numbers here are in units of watts per meter squared. And I'm going to dive in on the next slide into some details. But we essentially have a budget of what's coming in from the sun versus what's going out back to space in two different forms. One as reflected sunlight, and one as a completely different form of radiation that's generated within the Earth system and sent out to space. Plus some processes that are represented here that are not radiation, but important in the global flow of energy between the Earth's surface and the atmosphere. So here's some key concepts and terms that we're going to need today and throughout your work in this section of the course. On the left side of this figure in yellow is the solar, or what I'll call shortwave radiation. And that's really the energy source for the Earth system. That's where it all begins, is light that the planet receives from the sun. And this is not just visible light, it's also ultraviolet radiation and near infrared parts of the spectrum. Some fraction of what's coming in from the sun is reflected back out to space. And the reflection, as you see in the schematic, happens partially at the surface, but a lot of it happens in the atmosphere, bouncing off of clouds and other scattering objects in the atmosphere. A couple of important terms here. The albedo is a dimensionless number that's really just the ratio of what's going out, this reflected part, to what's coming in. Another important term, absorbed shortwave radiation, or ASR, is what's coming in, the difference between what's coming in and what's going out on this solar or shortwave part of this budget. And so if I take this number 340 incoming minus 100 watts per meter squared reflected, I get about 240 watts per meter squared. That is the net source of energy. That's how much energy the Earth actually captures from the sun. And we're looking in watts per meter squared because we're expressing all these quantities per unit surface area of the Earth. Now, on the other side of the budget, we see what we could think of as the sink of energy, how energy leaves the Earth system and goes back out to space. And so there's a number of different terms that basically mean the same thing: thermal radiation, or terrestrial radiation, or long wave radiation. Long wave reflects the fact that the wavelengths of the radiation are much, much longer than in this yellow part of this schematic. And that's really to do with the much cooler emission temperature of the Earth relative to the sun. Now, in terms of this balance of what the Earth receives and emits to space, the key number is this one at the top. And I'm going to give that a name, which is another important term here: outgoing long wave radiation, or OLR. And that's 239 watts per meter squared. Now, another key point here is that if you look in detail at what's in these orange arrows, you see that the Earth's surface is emitting upward a much larger amount of energy, 398 watts per meter squared. that number is much larger than this number. And so for reasons that have to do with the greenhouse effect that I'm going to say something about in the next slide, the emission to space is actually a lot smaller than it would be in the absence of these atmospheric processes. So hang on to that for one moment. But another key point, and the last key point on this slide, is that these numbers, the source, the net source ASR, and the sink, the OLR, are nearly the same, but not exactly the same, right? If I take the difference between this number minus this number minus this number and to one, I guess, one decimal place precision, the answer is a positive number, and it's 0.7 watts per meter squared, and that's listed here in the schematic as so-called imbalance. So the Earth is emitting less to space than it's absorbing from the sun. It's not a large number, but it's positive, and that means that energy must be accumulating within the Earth system. And that's actually what's driving the global warming that we are experiencing presently. So here's a schematic, again, from a recent IPCC report that emphasizes that same point, that in a stable climate that is not changing, the incoming and the outgoing energy balance each other. So ASR equals OLR in this schematic. But what's going on in today's climate is a small but persistent imbalance between what's coming in and what's going out, which is a little bit smaller. And so energy is accumulating, and the numbers here represent the fraction of that accumulation happening in different reservoirs. And the vastly largest share of it is going into the oceans, because it's the oceans that have the large heat capacity in the Earth system. So let's talk a little bit about the greenhouse effect. Okay, so the Earth's surface behaves basically like a black body, and a black body is governed by the Stefan Boltzmann law, which says that the radiation emitted by a body at temperature T is this constant sigma times T raised to the fourth power. And if you plug in typical numbers for the Earth's surface temperature here, you get something close to this value, 398 watts per meter squared. So the Earth's surface is emitting that radiation upward. But it turns out that nearly all of those emissions are actually captured and absorbed in the atmosphere and don't make it all the way out to space. And that has to do with specific molecular properties of certain trace gases in the atmosphere, notably water vapor, carbon dioxide, methane, nitrous oxide, and a number of others. These happen to have the right absorption features to very effectively absorb the types of wavelengths that the Earth is producing. Now, what's the consequence of that? The consequence is that energy coming upward from the surface of the Earth is being absorbed by gas molecules and water droplets in the atmosphere and being re-emitted, but it's being re-emitted at different temperatures than the surface. And the key point here is the temperatures in the upper troposphere, where most of this OLR, outgoing long-wave radiation, is actually generated, the temperatures are much cooler. So colder temperatures mean lower emissions, again, by sigma T to the 4. Okay, T is smaller, the OLR is lower. So that's the essence of the greenhouse effect. And it's because of that greenhouse effect, the Earth's surface is actually kept much warmer and more habitable than it would be if we didn't have an atmosphere. But what's going on, since industrial times is that we've been accumulating excess greenhouse gases in the atmosphere. So what does that do? Well, it actually causes that level of emission where these emissions out to space are actually being generated is getting pushed higher and higher as the greenhouse gases accumulate. And so the temperatures at which those emissions are occurring at cooler and cooler temperatures, because the air temperatures tend to get cooler as you go up through the troposphere. And so we raise the level of emission and we thereby reduce the OLR. And so we're reducing the OLR below its equilibrium value, pushing the planetary energy budget out of balance and causing energy to accumulate. Essentially, we've made the Earth less efficient at losing energy to space, and it has to warm up in order to regain equilibrium. So let's talk about climate models, okay? And we'll come back to the energy budget in just a moment. So what is a climate model? It's actually surprisingly hard to define, but I'm going to take a stab at it. So first, what is climate? What do we mean by climate? Well, essentially, we mean statistics of weather. So that could be space and time averages of air temperature and precipitation, but statistics can also be higher order statistics, such as measures of variability. Next, what is a model, right? The word model means a number of different things in the English language. In the general sense, we're talking here about a conceptual model. Conceptual model is a representation of a system, consists of concepts used to help people know, understand, or simulate a subject the model represents. Conceptual models are often abstractions of things in the real world. Now, climate models are abstractions of things in the real world, but they exist not just in our mind, but in the form of equations and computer code. So here's a quote from a very nice textbook called The Climate Modeling Primer by McGuffey and Henderson Sellers. Climate models are likewise idealized representations of a complicated and complex reality through which our understanding of the climate has significantly expanded. All models involve some ignoring, distorting, and approximating, but gradually they allow us to build understanding of the system being modeled. So pay attention to that focus on building understanding there. We'll come back to that at the end. But that's not a definition, right? That's a description. I'm going to take a stab at offering a minimal definition of what we mean by a climate model here. So a conceptual model rooted in approximations to the laws of physics that govern Earth's climate system. So climate models need to have some representation of the actual rules, like the laws of physics that govern climate at some level of detail. So this is different from the idea of a statistical model. A statistical model is taking data and fitting it to a theoretical probability distribution. That's not what we mean by climate modeling. We mean encoding some aspect of the laws of physics into equations and computer code. Now, more specifically, I'm going to define a climate model as a mathematical representation of that exchange of energy between the Earth system and space and its effect on average surface temperature. So a focus on this planetary energy budget is really a key feature of all climate modeling, because it's, as I've been emphasizing, it's imbalances in that budget that drive climate to change. Why surface temperature? Why is that the most important variable out of all the many things we could measure or quantify in the world? Well, a little bit arbitrary, but it is where we live, right here on the surface. But temperature, and specifically temperature at Earth's surface, is just fundamental to many key climate processes. And so it's sort of a proxy for many of the controlling factors of many of the Earth system processes that actually affect the planetary energy budget. So that's where we start. So let's talk about some real basic ideas in modeling the Earth's energy budget, and this will hopefully set you on a useful path for some of the exercises you'll be doing in the Climate Match Academy. So we can write down a statement of energy conservation for the total energy budget for the Earth system. So E here is some measure of the heat content of the whole system. So that's all the oceans, the land surface, the ice, the atmosphere. And the statement is just that E has to change if there's an imbalance in what's going in versus what's going out. So dE by dt equals ASR minus OLR in units of watts per meter squared, as we've already been working with. So we've been looking already at this imbalance. It's about 0.7 watts per meter squared presently. I want us to pay attention here to the fact that this very simple equation, this simple statement of a physical principle, energy conservation, takes the form of a differential equation. There's a time derivative here. And the vast majority of the physical laws that come to bear on climate processes are expressed in the form of time derivatives, right? The physics tells us how quantities change in time with respect to each other. And it's that time derivative that's going to let us peer into the future. In this case, the statement is just Earth is absorbing more shortwave than it's emitting as long wave, so E must be increasing in time. But if we want to be quantitative and actually solve equations for a climate model, we're going to typically need to use a computer, and the computer only deals with discrete numbers. So I want to just say a couple simple things about this idea of discretization. So we have to approximate time derivatives in some form of finite difference. And I've written here a formula for the simplest way you can possibly do that, which is known as the forward Euler method. And there's entire books and entire careers spent on studying numerical methods for differential equations, but this is enough just to get the concept in place. So I replace my time derivative with a finite difference, and the difference delta here is the difference between the quantity at a future time and the quantity at a present time. So this is my left-hand side of the equation, and that has to equal the right-hand side of the equation. It's the physical statement of energy conservation. If there's an imbalance, then E has to change. But having written in this discrete form, I can now rearrange this equation to solve for E future, right? This is my prediction formula to say I can take my knowledge of the present conditions, my knowledge of the present imbalance, and I can multiply by delta T and make a prediction into the future. Okay, so if I know those things and I make a choice for delta T, and delta T I'm going to call the time step of my model, I'm typically measured in seconds here, then I can actually plug in my known quantities and make a prediction. And my prediction is specifically for some moment in time in the future, a distance time, delta T, stepping into the future. So we're going to call this stepping forward in time, or time stepping. And the vast majority of climate models use some form of this kind of numerical time stepping. So think of delta T, the time step, as basically the smallest unit of time that's represented in the model. So any process that may be occurring in the Earth system on faster timescales cannot be directly simulated or represented. We must make some approximation to get, in a statistical sense, the impact of those faster processes on the things that we're resolving. And that's what's known as parameterization, which hopefully you'll dig into a little bit later. So we don't have a climate model yet. To turn this into an equation I can solve, I need to relate all the terms in my physical budget statement to state variables of the climate system. So let's think about temperature, right? Temperature, as I said, is a key factor in most climate processes. And in the terms that are already in that equation I wrote down, temperature is involved in every single one of them. So for example, E, the energy content of the Earth system. Well, a lot of that is in the form of internal energy of fluids. So the ocean and the atmosphere have internal energy. It's proportional to temperature in a fluid, right? So if I raise the internal energy of the fluids through radiative imbalance, I'm going to increase the temperature of the fluids. The water gets warmer, the air gets warmer. The terms on the other side of the equation are also affected by temperature, right? So ASR, my absorbed shortwave radiation, depends on the planetary albedo. The planetary albedo itself might depend on the distribution of surface ice and snow, which depends on temperatures. It might depend on clouds, which are a product of the hydrological cycle. Many temperature-dependent processes are involved. My OLR term, even simpler. I can just think about the Stefan Boltzmann law. That's certainly not the only bit of physics we need in a full complexity climate model to represent long-wave radiation, but it's a good starting point. Warmer bodies emit more radiation to their surroundings. So there's a temperature dependence in that OLR term. So I can think about what might happen if I represented, by bringing some more physics into this model, the role of temperature in each term in this equation, and I go through a process of moving forward in time. So initially, as we've said, ASR is greater than OLR and E has to go up. So the very first time step, I would get a larger E, right? And that would cause the temperatures of the atmosphere and ocean to increase. If I wanted to take a second time step, then now the situation has changed, and I would basically need to recompute all of the terms in that equation, right? Because the warmer atmosphere is now emitting more radiation to space, so OLR is larger. Perhaps there's less ice and snow, a lower albedo, and so ASR is also larger. So the imbalance between those two terms might have changed. And so the change in temperature I will get at the next time step would have to be a little bit different. So I'd like to ask, where does this go eventually? Does the temperature stabilize at some stable equilibrium value? And that's the kind of thing that if we could be a little more quantitative and put temperature dependent formulas into each of these terms, we could actually investigate on a computer. And that's the kind of thing that you will be doing in some of the exercises coming up. But we need to put some more physics into the model in order to do that. I'm going to set that aside for now. Just hope that's a useful orientation for what you'll be doing in the course. But I want to talk a little bit about the shape and size of climate models as they exist across the spectrum of complexity that scientific community works with. So complexity is necessary, right? The climate system is an extraordinarily complex system. And one of the key roles of climate models is to quantify credible projections of future climate change. And to do that, to build confidence in those projections, we need to put as many processes into the model as we can fit if those processes have some important impact on the planetary energy budget. I'm going to elaborate that on the next couple of slides. But there's tension between that complexity and the scientific prerogative of simplicity, right? Science has an obligation to seek simple answers to questions where possible, right? And that's how we build understanding. And so I'd like to paraphrase a common statement here. All models are wrong. Some are more useful for certain applications than others, is how I'd like you to think about this next set of things I'm going to say. This is a schematic, another complicated schematic from a recent IPCC report that emphasizes a number of different processes that drive climate change. And by drive climate change, as you've been following what I'm saying, we're really talking about pushing the planetary energy budget out of balance. And lots of processes here, lots of arrows and different physical systems involved. Okay. There's a lot of complexity to how the atmosphere works and how it interacts with the surface of the earth and so on. And another way to think about this question of what needs to be in a climate model, I like this schematic also from an IPCC report because it lays out a time axis here. So I've got a bunch of, again, a schematic of lots of different processes. The plus and minus signs here are meant to indicate feedback processes. A feedback is a way in which a process either amplifies or damps a climate change that's driven by some external forcing. And the idea of this figure is that there's lots of different important processes, but they operate on very different time scales. And so we have a scale going from hours out to centuries here. There are atmospheric processes that affect radiation on timescales of hours. But there are also things like the circulation of the deep ocean and the dynamics of land-based ice sheets that all in various ways impact that planetary energy budget by moving energy around, by changing the albedo of the surface, by setting different radiative properties of the atmosphere, but do so on different time scales. So the question of what needs to be in the model is often contingent on what time frames we're interested in studying. All of these processes, all this complexity is kind of coupled to itself. And one of the great sources of complexity is the fact that all these processes exist in moving fluids. Right, so the atmosphere and the ocean are fluids that are moving all around the earth and they're moving information around. And so a climate model typically has to solve the equations of motion for moving fluids on a sphere, on both the atmosphere and an ocean. And that involves discretizing not just in time, but in space. And so there's a schematic here of kind of what it looks like if you take the Earth and you chop it up into boxes. And in some sense, that's what a climate model has to do in order to take the partial differential equations of fluid motion and solve them. Another thing to think about here is time stepping. And what a climate model typically needs to do is resolve the motion of weather systems, because it's those weather systems that are moving a lot of information around about conditions in other parts of the planet. And so the climate model needs to resolve the weather in order to simulate the climate. And that means short time steps. There's lots of other equations involved, like the governing equations for radiative transfer, processes in cloud physics, processes at Earth's surface. And in the space of Earth system models, we're coupling even more processes together, which become, again, relevant on longer timescales. Things like how vegetation distributions change as the climate changes, or how the chemistry of how carbon cycles through land and ocean. And so the more of these processes we couple together in a system that has to basically solve the weather as we step forward in time, we're looking at an enormously challenging computational problem. And so computer power has always been a limiting factor in climate modeling. So this is just kind of a nice historical schematic of how this field has developed over time. In the mid-1970s, the first computer-based climate models started to appear. And this kind of marches through generations of models up until, this is not an up-to-date schematic, this is sort of one generation behind where we are now, but this gives a sense of the types of processes that were typically included in state-of-the-art computer models of climate of those eras. And the thickness of these cylinders is meant to schematically represent the level of detail, the level of complexity, the spatial resolution, and so also the amount of computer power going into each aspect of the simulation. So one more little fun teaser, again, from IPCC report. This is kind of the surface of the Earth as seen by a climate model. So this is a map of Europe, but it's a map of Europe at two different spatial resolutions. So if we chop up the Earth into smaller boxes, then we see a lot more detail. Okay, so if we run a simulation with this grid, then the atmosphere that's blowing over these mountains doesn't know anything about the detailed valleys and ridges that appear here. So does that matter? Well, again, it depends on our application. But if we think, for just to throw out an example, if we think about the storage of snowpack in mountains associated with snowstorms interacting with the topography of a mountain range and the seasonal distribution of water that results from that, then this kind of thing might be important. Okay, so simulation for prediction requires complexity in a nutshell. But where does that leave scientific understanding? And I want to say a few words about this idea of using models as laboratories. We build understanding of processes often through the construction of carefully controlled experiments in much the same way a laboratory scientist would do. And that often means comparing one simulation against another in which we've controlled conditions and changed one experimental variable. And it's often the case that doing this in the context of simpler and more idealized models can be a better way to achieve some scientific understanding. There's two kind of classes of reason for that. One is just practical. Simpler models tend to be easier to run on smaller computers, and so that enables the working scientist to do more investigation. But the other one is just more of the idea of interpreting the result. A simpler model is easier to understand why the model did what it did. And so often we have an easier pathway to extracting some learning. And so we often take the results of simpler model experiments and use them to build understanding that we can then bring to bear on more complex representations of the climate system. And so a term that gets used a lot in this context is mechanism denial. And that's this bullet point here. Removing a process from a model can be a way to measure its impact. If we compare a simulation with and without a process, we can see sort of the global impact of that process as its effects cascade through all the other elements of the model. And so in science, we're often talking about hierarchies of models, which refers to this spectrum of complexity ranging from things that exist on pencil and paper all the way through to the highest complexity computer simulations that depend on the largest computers that we have on Earth today. So I just want to throw out a couple of teasers that come from my own work, just illustrate a little bit of that more sort of creative side of the application of climate modeling to investigating science questions. So I'm interested in ocean circulation and how it interacts with sea ice and how those interactions regulate or affect global climate. This is a video I'm going to show that stems from a study I did about 10 years ago, where we were interested in studying how the Earth system might be able to flip from warm conditions with no ice at the poles to cold conditions. And so I'll start the video. The video shows the output of some simulations where we turning down the output of the sun, right? As a modeler, you get to turn knobs if it's useful to you. And the knob here is just how bright is the sun shining over the course of many thousands of years here. So we've turned down the sun and then we've turned it back up. And what's shown there's a lot of graphs here. These are views of one pole of the planet. And one thing you can see here is the geometric simplification that we used in this study. I'll play the video again, but we've simplified the geometry of the Earth system here. So this is a simulation of a planet that's Earth-sized and has a lot of the same property as Earth, but doesn't have the continents that we know today. It has just this one strip of land that goes from one pole all the way to the other pole. And so the whole planet is an ocean, but it's an ocean that's bound into a basin. And so it obeys some of the same physical constraints as the real ocean basins that we have on Earth today. One of the neat things that came out of this study that I'll try to emphasize on this second run, as we turn down the sun, what you're seeing here is sea ice growing on a pole. And sea ice starts to grow and it does some complicated things, but a large ice cap appears. But this exhibits what we call hysteresis. So we've turned a parameter down and then returned it to its reference value. And if I scrub back to the point of the video where we were back around the reference value and pause, we've gone from a warm climate to a much colder climate with a radically different distribution of sea ice. And so we used here a geometrically simplified model in order to do some curiosity-driven research about mechanisms by which the Earth system might be able to transition between warm and cold and might be able to support more than one stable equilibrium, more than one stable solution of the planetary energy balance, all else being equal. One more example on a similar theme, showing a different kind of idealization. So here I'm going to show another video of another kind of simulation with a much more realistic model. What you're seeing is the sloshing around of the seasonal cycle, where the colors represent the sea surface temperature and the white represents snow and ice. This was asking the question, so we know that the ocean circulation plays an important role in determining the shape and size of the sea ice cover, and the sea ice cover in turn plays a hugely important role in determining global climate through its albedo and other properties. And so this is asking the question, what if there were no ocean circulation? So this is an extreme mechanism denial experiment. I'm going to simulate a planet much like Earth, but in which the ocean is sort of static. It can't move. So it's just exchanging energy and water with the atmosphere, but it's otherwise not moving. And so this simulation shows what happens over the course of 50 or 60 years when we swap out the real ocean for this 50-meter swamp. And what's happening here is that there is a seasonal cycle continuing to oscillate, but the planet is cooling down radically. The sea ice is growing into the subtropics. And in fact, the planet cools by about 24 degrees. And so it lets us quantify in one number effectively what is the impact of ocean circulation on climate today. Well, the Earth is 24 degrees warmer than it would be if the oceans weren't moving. Okay, so that's a sort of extreme example of a way we can use a mechanism denial experiment to quantify a question about the impact of a process. Okay, so summary of this lecture, summary of the key points I've tried to make. Climate change is driven by imbalances in the planetary energy budget, imbalance between absorbed shortwave radiation and outgoing longwave radiation. Greenhouse gases reduce the outgoing longwave radiation below what they would be without the gases, and adding more of those gases reduces the outgoing longwave radiation further, pushing the planetary energy budget out of balance. A climate model is a representation of that planetary energy budget through approximations of physical laws. Complexity is needed in climate models, and the main reason is that many Earth system processes affect that energy budget on many different timescales. But at the same time, models are laboratories, right? They're virtual laboratories for exploring scientific questions and building understanding. And scientific progress, in fact, often does depend on judicious application of a hierarchy of models and a comparison across that hierarchy in order to build solid understanding of complex processes. And with that, thank you for listening, and I hope you find this section of the Climate Match Academy illuminating and interesting, and I wish you good studying.